Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Muchas gracias. Esta es mi primera vez en Cancún y en el estado de Quintana Roo, aunque he estado en México varias veces, y es un gran placer para mí visitar esta zona y muy bonita. Me gustaría poder estar más tiempo, pero por lo menos he podido ver algo de la selva. So, I will be talking in English, so I'm sorry about that. I was wondering how to translate some of the terms, and I realized that I didn't know, so I figured this would be easier, plus there are some people that would benefit from it. So today what I'm planning to do is try to convince you that if you're trying to build a speech system, image processing system, or maybe other machine learning system, that you give serious consideration to deep neural networks. And I will try to hopefully convince you why you should do so. So I will initially start talking about just an introduction to neuroscience, so I'm trying to assume that you don't know necessarily a lot about this. If you do, you may get a little bit bored. Then talk about artificial neural networks. They've been around for a while. And then the latest generation of neural networks, which is called deep neural networks. I will explain why it's called that way, and the application to speech recognition. So first, let me start by showing, that was a picture. This is me. In 1990, this is an office in the basement of one of the Carnegie Mellon University buildings. And why am I showing you this? Because I want to give you the biggest evidence for you to believe me that deep neural networks is big. And the reason is because I was doing my thesis at that time on noise robustness for speech recognition, how to build speech recognition systems that are more robust to background noise. And one of my office mates, Yoshiaki Oshima, was trying to work on the same problem, but he was looking using a different set of techniques. Well, I was using more like what I would call now traditional machine learning. He was looking at neural network-like systems, modeling the human auditory perception system. And at that time, I graduated that year, and we started at the same time. He stuck around for a few more years, eventually graduated probably because he had to graduate, not because he had solved the problem, made much progress, which meant that from that point, I say, I'm not going to touch neural networks. This is not something that works. This is a problem. And now I'm a convert. So I hope this is the biggest piece of evidence for you that you should pay attention to this, because back then, I did not like neural networks. I didn't think that they would work. And the reason is because I saw him crying almost many times, struggling with the learning algorithms, trying to build the systems. I said, well, this is not going to work. This is too complicated. By the way, if you use some of the speech systems today in some of the phones or even Kinect, you will realize that we still have not solved the problem of doing speech recognition in the presence of background noise. It's still a problem. And maybe there's a correlation, because the papers that I published on this topic were accepted, whereas the paper that we tried to publish on Kinect was rejected, yet that thing worked. So maybe there is a pattern here. I'm starting to get worried, but hopefully now 20-some years later, we will figure out some way to make these systems work. So let me start by describing how neurons work, since that's the foundation for neural networks. And the human brain has about 100 billion neurons. And each neuron has about 7,000 on average synapses. So this is a diagram of a neuron. This is the body of the neuron. And all these things are the dendrites. They are kind of like the inputs to the neuron. And then here is the axon, and here's the output of the neuron. So one way to look at this would be saying we have a system that takes all the inputs, which are the connections from other neurons, puts some weights, which is essentially the synapse or the connection between one neuron and the next with different strengths, and subtract some term. And then they go through a sigmoid. This stands for the sigmoid function, which is this type of function. And this type of function, what it does is that if the signal is the combination of signals is much bigger than the threshold, it will produce a 1. And if it's smaller, it will produce a 0. And in between, it's kind of like slowly ramping. So it's trying to produce a nonlinearity, either 1 or 0, and that there is evidence from neuroscience that that's how neurons work. There are many in the brain, and that's something that you will see is different in the systems that we build, the artificial systems, but it's interesting that they are slow. I mean, we are used to thinking, okay, we need fast compute power, gigahertz. Well, it takes about a millisecond often to produce a system, an output. So how is it that they can be so powerful? We use them for lots of things, and it's because we have 100 billion of them and lots of connections between them. They're also non-deterministic. This is not like a computer program that will, with the same inputs, will always give you the same outputs. There will be some random components, like spikes firing in and out at different times, and you will get different results. So that's something to keep in mind, because that's not necessarily how our artificial neural networks work. So why, I became interested in neuroscience after we started getting good results with these deep neural networks. But I can imagine that there are reasons why you may be intrigued in learning more. There are mysteries here. Like, what is the difference between the brain of a human and the brain of a primate, a monkey? We see the evolution. Well, we have a larger brain capacity, like about 3 times bigger. Is that it? It's just because we have a bigger brain? It can't be just that it, because whales have bigger brains than humans. They don't seem to be as smart. Or even elephants. Maybe the number of neurons? Well, elephants have as many neurons as we do. So what is it that it makes us intelligent and they don't? That's kind of an interesting question. Also, there are like things of interest in medicine. Can we cure Alzheimer's? We often know of someone in our family, extended family perhaps, that has this disease, and many others. So there are lots of interesting things that maybe we can learn by looking at the problem differently, not just from the doctor medical aspect, but by looking at it from the computing point of view. So what do neurons do? Well, neurons are built to pick up patterns. They see something that happens frequently and they memorize it. The Hebbian rule, created by Hebb back in the 40s, says neurons that fire together, wire together. Means if the input is on and the output is also on at the same time, the connection between those neurons is going to increase. The weight of the synapse is going to increase. And that appears to be from neuroscience, how our human neurons work, how we learn. One thing that is interesting is the number of synapses or connections. You can see as the wiring of our brain. When the babies are born, we have a number of them. We get the maximum after 2 years, and after that, we get fewer. And that's because there is constant creation of synapses, which is connections between the neurons, and also destruction. So what happens here, after it's stabilized after 4 or 5 years old of age, you create as many synapses as you destroy on average. So it's not like you have the same forever. You create new ones and you destroy someone. So you learn something and you forget something, basically. So this is the motivation from the neuroscience point of view. So then Rosenblatt, back in 1958, proposed the perceptron. And that was the birth, really, of artificial neural networks. So what is the perceptron? So the perceptron is basically a linear classifier. That's one way of looking at it. Let's say that you have points. If your feature space has 2 dimensions in this case, you have feature points here and feature points here represented 2 different patterns, maybe like circles and triangles, for example. And what you want is to find a line that would divide and classify both of them. So this would be, in this case, that line. And it would be maybe W1 times V1 plus W2 times V2 equals V. And that's the line. If it is on one side of the line, you say, well, it's a triangle. If it is on the other side of the line, then you say it's a circle or any other. Well, you could also build this classification with a sigmoid function. You have this term, which is this. And if it is larger, then you say it's a 1, maybe it's a triangle. If it is smaller, it's the circle. This is exactly the function that, the sigmoid function that neurons use. So how do we learn? How does the system find those weights that do the classification? Again, we have here the example where, in this case, we have 3 inputs with different weights, and go to this neuron and produce an output H. So the way we learn is if we are given a few samples where we have some inputs V and the corresponding label, what the system should do. Then we can compute the error. The system computes the difference between the H and the value of the neuron and the label. And you can square them and add them up over a number of samples. And what you want is to find the weights that will minimize that error. So H is the sigmoid function of this. So what you can do is gradient learning. The weights at that iteration equal the weights at the previous iteration minus some constant times the derivative, the gradient of the error over that weight. And if you do the math, take the derivative of this, you get this function here. And this is the derivative of the sigmoid, which has this form. What this means is that in this region here, which is up there, the gradient is basically 0, so you can't really learn anything. Same thing here. So the only time where the gradient will be non-zero and the weights will change is in this region here. So perceptual learning is trying to find a local maximum. It's doing hill climbing. So imagine that you have a surface, say these are the 2 dimensions. If you start here, it will hopefully get to this point. If you start here, hopefully it will get to this point. But it's not guaranteed to find the global optimum. It will find a local optimum. This is just an illustration in 2 dimensions. But typically the systems use thousands or even hundreds of thousands or more inputs. So this surface is like in a very, very high dimensional space. And it's going to have lots of local optimum. And whatever these algorithms will do will find just the local optimum, not the global one. There was a paper in 1961 by Minsky and Papert that essentially started the winter of artificial intelligence and the winter of neural networks. What it did is in that paper, they said, well, there are some functions that are very simple, like the XOR function, which cannot be modeled by a single perceptron. Like this is an example where you have circles, and the triangles. There isn't a single line that will classify both of them. They did not say that neural networks would not work. They just said that a single perceptron would not work. But the community read this paper and stopped working on neural networks for like quite a few years because they misinterpreted, and Minsky was one of the founders of artificial intelligence, so he had a lot of credibility. So artificial neural networks, the idea is, well, not put just one perceptron, put many of them. So here we have many inputs, here we have many neurons, and we have different layers. Not just one, but many. If you do that, then you can learn the XOR function and many other functions. Here I use a notation of 1 to absorb the term B that was in the equation before. So it's kind of like an input that is always set to 1, and you learn all the weights. Interestingly enough, Alan Turing already proposed artificial neural networks back in 1948, but he had not done all the mathematical derivations. So how do you train these networks? So there is an algorithm called backpropagation. And let me explain intuitively what it does. So this is, in this case, one neuron, and we have another one. So the output of this one is the input of the next one. So if we look at what this produces and we compare with the true label, what we like is to adjust the weights of all of our network to minimize the number of errors. And the way we do it is similar to before. We compute the error function as the sum of the square terms. And now we take the gradient and we take the derivative. But when we take this, it's easy, right? But when we're trying to learn one of this, we need to see what is the impact on the error here and here. We backpropagate the error, and then from here down. And that's essentially using a very simple idea in math, which is chain rule. So you take the gradient, is what we had before, times this derivative, which is this term here. This, again, will find a local optimum, will not find the global optimum. But this surface, these functions here, can do an arbitrary difficult classification problem, at least in theory, assuming that you don't get stuck into a hill-climbing local optimum. So this is an introduction to artificial neural networks. And they were used mostly in toy problems. And the community started using it for speech recognition back in the late 80s. And you see a few examples. There was a lot of activity in the late 80s and early 90s in using artificial neural networks for speech recognition. But then the second winter of artificial neural networks came. And this time, it was not sudden. It was not like a famous guy published a paper saying this is not going to work. What happened is that there was another technology called hidden Markov models, short HMMs, which became the dominant technology in the 1990s, mostly because at that time, the accuracy of the systems, an HMM or artificial neural network was about the same, but HMMs were faster to train. And there was more and more data available during that time. So the artificial neural networks guys could not train with all the data. So they had to train with less data, and therefore they started doing worse. Whereas the HMM community could train with all of the data, and they did better. So that's why artificial neural networks fell out of favor in the 90s. But then there was a renaissance. Again, this is like the cycle. And it happened around 2006 when an expert in machine learning, famous person called Jeff Hinton, invented deep belief networks or deep neural networks, which is the new generation of neural networks. And I will try to explain what they are. What he was trying to look at is the fact that a lot of the times when you're training these networks, you get stuck into a local optimum, in which in some cases may be very bad and very far away from the global optimum that you want. So it was very important to get a good initialization. So he says, well, I'm going to initialize, rather than initializing their weights randomly, as many people have done before, he decided to come up with a new algorithm called Restricted Boltzmann Machine, RBM, which had been proposed early on, but now was rediscovered, and use that to do a better initialization. And once he initialized that, he did backpropagation as before, and he tried that on a task called MNIST, which was a set of handwritten recognition digits, things like this, and got the best results published at that point. So one of the researchers in my group came to me in 2008 and saying, Alex, I would like to work on this problem. And I said, well, but you're in the speech group. And this is image processing, doesn't make much sense. And that's where one of the things that we value about MSR, you need to trust the intuitions of your researchers. So I said, I'm not sure I'm convinced. Plus I had bad memories from the neural networks days, but it's okay, you can go ahead and explore it. So he started playing with that and became excited and started getting great results, mostly again due to the good initialization. And then he started applying them to speech. So eventually he started playing with speech. So what are these RBMs and why I all of a sudden became much more excited and a believer in these deep neural networks? So imagine that V is the input and H is the output of a network. If you have a probability density function that looks like this, that's an exponential model or a log linear model, where E is the energy function, which is a dot product of a set of weights B and the visible V, weights C and the hidden values H, and a product with a matrix weights here. It turns out this is a normalization context. It turns out that if you compute the marginal, what is the probability of seeing the hidden values to be 1 or 0, given that you've observed these visibles, you can do this and normalize. If you follow the math, it turns out that you get this, where this term is a sigmoid function. And that's why I say, this is interesting. One of the reasons why I didn't really like neural networks before is because there was this sigmoid function that I thought that was just coming because that's what our neurons use, but I didn't know what they meant. There were all these learning rates, all this initialization, I didn't understand. But now, what we see is that this function is not just a coincidence. It's what you get when this is your probabilistic function between the inputs and the outputs. It's still the same function, But now you can interpret things differently. We can bring to bear all that we know about probabilistic processes, machine learning, to this problem. So now if we can formulate it this way, we can say, well, we can try better initializations, other types of systems, and that's what we started. By the way, this has the property that the posterior probability of the binary visible units is also a sigmoid. So you can go this way and that way too, and it's the same function. Interesting. And this is true even not when the inputs are binary, but also when they are Gaussian. Same thing. So this had like very nice foundation, which on its own has not improved our accuracy or anything, but allows us to look at the problem differently than before. So one example is we can say, how about if we use maximum likelihood estimation, a very typical technique for estimation used in machine learning. So what we like to do is learn the parameters of our system, C, B, and W, that maximize this probability. And, well, we can try to do that. That may be like a good initialization, better than random weights. The only problem is that this is highly nonlinear. But at least we know what we're trying to do, and we can use some other techniques. I'm not going to go into this other than say that there is one method called contrastive divergence that will let you go iterate back and forth and learn through maximum likelihood those parameters. I will only mention one equation here and the interpretation. What this is doing is iterating with the product of the input and the output of the neurons from the data and what the model says. And you want this to be 0 eventually. If you think about this, this is back to the Hebbian rule. If two neurons, if the output of a neuron, that is the input of the next one, and the output fire at the same time, they're correlated, there's like a pattern there. That's what this is measuring. So everything seems to be fitting together. What the neuroscience did back in the 40s, Hebb, when he proposed his rule, the sigmoid function that the early guys, Rosenblatt and others, had done early on, and this in a probabilistic formulation. So that was kind of interesting. So what we do now is we do this RBM, restricted Boltzmann machine training, and then we do the backpropagation from that point. And we think that that provides a better initialization. So how did we use this for speech recognition? So in speech recognition, we have still hidden Markov models, which is a sequence, a network that has states where at every time frame, you can go back to the same state or transition to the next one. Stay in the same state or transition to the next one. And when you're in that state, you emit a symbol. This is, for instance, a spectrogram, which is a time and frequency representation of speech. That's the model that we use, hidden Markov models that we use typically for speech recognition. So here, the output probability was modeled as a mixture, as a sum of Gaussian density functions. Now what we did is say, well, let's replace that by a neural network, a deep neural network like that, like what I just described. And everything else is the same. I'm not going to go into the details of all the parameters. Suffice to say that we did this with a state-of-the-art system, with all the bells and whistles that you can imagine, pretty complex system. And there were a bunch of experiments that my colleagues, Franz Seidel, Dongyu, and Gangli did on switchboard. And what you could see, switchboard is a standard database that the Department of Defense has set up that contains lots of people talking casually with one another. And here what we have is the performance of the system, the best system for this task. And after we use the new deep neural network, we go down this much, which is 33% relative error rate reduction. This is another test set, 32%. Normally, this is unheard of in the field of speech recognition. We rarely see from one technique getting such a big improvement. So we were very excited. So when Li Deng, who's the first person that was working on this, told me this, I said, check, you must have a bug. This is too good to be true. But, had several people validate it, and in fact, it was working that well. We tried on different tasks to see if it was just something peculiar for that task. We also got 22% error rate reduction, 26, 28. So it was just helping all across the board. So why is it that, that this type of techniques work so well? What was new? I mentioned the restrictive Boltzmann machine, the initialization. Was that the only thing that we did? And I'd say probably not. I think the most important thing is the increase in computing power. We know about Moore's law, and in 20 years since people forgot about neural networks, Moore's law has grown dramatically, right? So now the computation that is available is much, much higher than before. And what happens is that these algorithms are very computationally expensive to train. The runtime is fast, but the training is slow. And now we have a lot more than we had back then, so we can go and revisit old ideas. So that's by far probably the largest contribution. That alone is not sufficient. What that allows us is to run more experiments. So now we can try many more experiments, different combinations, and many of them don't work, but some of them do. So sometimes don't get discouraged. If there is some technique that you're fighting with that seems too slow now, well, maybe at some point in the future, the computing increases, and all ideas are old but not necessarily bad. That reminded me when I was talking to Vishnu et al., who worked at Bell Labs for many years, and he was the inventor of the KELP coder, speech coder, which is, by the way, used in every cell phone that you have today. And at that time, he told me, well, you know, I never filed a patent for this, because when I first came up with the idea, to compress 1 second of speech, it took me 4 hours. So I said, well, this will never be practical, never. So you never know. These kind of things, sometimes computation is just intractable at that time. Maybe it's going to go beyond your PhD thesis, but there will be a chance to revisit it later. So even despite the fact that we've made a lot of improvements on accuracy, like 25, 30% in reduction in error rate, training is still slow. We still need GPUs, which are very powerful lots of processors to train this, and we can still get stuck in a local optimum. So this is another problem that we still haven't solved. Since we started publishing results on speech recognition a year and a half ago, there was one paper. The following conference, there were like 5 papers, half of them ours. And then last year, there was like 20 papers, and just a month ago, there was like 40. This field is growing like crazy. So this could really be an inflection point. And it's not just in speech, also in a lot of applications in image processing as well. So that's why I hope that you will give serious consideration to these kind of techniques. So this brings me back to thinking neural networks. There's the natural ones, and there's the artificial ones. Are perhaps artificial neural networks better than natural neural networks? And normally I would say no way, because we have natural neural networks, and we do a lot of experiments like that much better than machines. But the other day I was reading something about the results, the test results of high school students in the United States. And I was starting to get some doubts that the natural are always better, maybe on average or some cases. For example, I saw this problem, and everyone in this room, of course, knows the answer to this. Yet our prototypical student, this is what he did. Find X, here it is. Unbelievable, right? So maybe artificial are not so bad. Or another question, when they were asking them, what is the language spoken in Latin America? Our bright high school student answered, Latin. So it may be okay. Planes don't flap their wings, or maybe they did way back when, and they can fly faster than birds. So it's not always true that we need to copy or mimic nature to build these artificial systems. But it surely has some, excluding these high school students, by and large, machines do much worse for these tasks than humans. So in human intelligence in particular, artificial neural networks might do someday better, and there are some folks predicting that that's going to happen one day, but not yet, and perhaps not in my professional career. But for now, artificial neural networks have a lot to learn from nature. And since we've been getting these great results, I've been learning about neuroscience, which I found fascinating, regardless of the fact that we're doing this for speech recognition. And found out that there are a few things that our systems don't do. And I wonder, is it just because they're flapping their wings like this or flying and we shouldn't copy that feature? Or is it because it's there for a reason? I mean, we look at evolution. Darwin taught us that there are many things that happen, but they are not an accident. There are many accidents, and the ones that work well, there are those mutations that stay. So the randomness is one example. So randomness, we see that all these neurons produce random results. It's not deterministic, but our systems, if you put always the same inputs in, you get the same output. You think that that's a desirable property. Why is it that human natural neural networks have this randomness? I wonder, perhaps it is because that way they don't get as easily stuck into a local optimum when they're adjusting. Or local learning. I mean, there is evidence to say that in our neurons, we do not have backpropagation. All the learning is done totally local, meaning each neuron is learning exclusively by looking at its neighbors. So a neuron looks at the inputs and looks at its outputs and determines the synaptic weights. That way, it has no idea about anything else. But that's not how we're training our systems. So I think that there is a lot of work that we can do, and I hope that some of you will be motivated to work on this problem, to borrow some of the features, maybe not all, but at least explore some of the features of the natural and the human neural networks to build our artificial ones. And I'll close by saying that this still gets me a little bit worried because a lot of these papers that we've been publishing have been accepted. So maybe we still haven't figured out what is the right problem, but I hope that will happen soon. Thank you very much.
Thank you very much, Alex. I think we have time for one or even two questions.
You can ask in Spanish if you want.
Any questions? Okay, there is one. Please, Mike.
Is there any question as with the deep networks, as there is sometimes with the normal backpropagation or perceptron, about having too many degrees of freedom for some problems, for simple problems, for pattern recognition?
That's a good question. I'll answer one that I neglected to answer before. Deep. Why is this deep? What is the issue with this? Deep refers to the fact that there are many layers. Typically, in the past, when people had built artificial neural networks, there were a maximum of 3 hidden layers, 2 or 3. So, but just calling deep because it has more seemed at first to me a little bit presumptuous. It's like, just add more. What's the big deal? What happened is that, as I mentioned before, the gradients that propagate quickly become 0. But not here. In this case, this is the first time that we can learn networks with many layers and still learn them. And that's because of this new discovery, this RBM. So that's one thing that I forgot to mention. What you mentioned then is like the number of degrees of freedom. What happens if we put too many layers? Interestingly enough, what we found for the data sets that we looked at is that it saturates the performance. It doesn't get better, but it doesn't get worse, typically. So these systems appear to be robust. They don't overtrain. We would have thought a lot of machine learning systems, they would overtrain when you do that. And there is some of this to some extent, but by and large, they are much more resilient to overtraining than most of the neural network systems that we've built. I mean, traditional machine learning systems that we built before.
Okay. Thank you very much, Alex.
You're welcome.